All right, seniors, hope you guys are doing good. Big shout out to you. Hope you guys are staying safe. I am actually going to do this real quick just to make sure that everyone can see me there. Hello, for this, your third pre-cal class. Just a quick reminder, I am receiving the assignments that you have been sending me. I sent the message explaining that I don't want you to email me everything just yet. The assignment, the work that I assigned the other day and the work that I'm going to assign now, I want you to send that in one email, okay? And then in the virtual classroom, I'm going to kind of explain what we're going to do to kind of keep figuring out a way to keep sending the assignments for the time being. Today's topic, ladies and gentlemen, is or continue to be transformations. This is in your textbooks. I'm going to be explaining examples 5, 6, and 7 from page 202 through 204. And then at the end of the class, I have your final exercises for the week. Just continue to send me the emails to both email addresses I gave you. And so let's get started with this real quick. So in our previous video, we talked about horizontal shifts and vertical shifts, and we talked about reflections. Well, today we're actually going to talk about 2. In reality, there are 4, but what I just did is I just kind of compressed them so that way it'll be a lot easier to understand. We're going to be talking about horizontal stretches and compressions and vertical stretches and compression. In your textbook, they call them shrinks instead of compressions, but it's the same thing, guys. It's just, I guess, a preference thing depending on the book the version of the book that you're using. So let's talk about a vertical stretch real first. A vertical stretch or shrink. Now, this is the way that the function is expressed: y equals f or c times f of x, where c is actually a constant and f of x is a function, be it quadratic, linear, square root, or any other function that we have been or we can think of. And it's telling us if the constant is greater than 1, then we say that is a vertical stretch by a factor of c. And let me write that of c because it kind of looks, I forgot. All right. Anyway, and it says that if c is greater than 0 but less than 1, then we have a vertical shrink or compression of a factor of c. Now, this one is a little bit tricky because you're thinking when you read this for the first time, what do you mean greater than 0 but smaller than 1? Well, greater than 0 but smaller than 1 actually refers to fractions. So what this is trying to tell us is that if there's a fraction in front of the function, then you're actually going to perform a vertical shrink. If there's a whole number greater than 1 in front of the function, then you're actually stretching. So let's take a look at the first example real quick. Example number 5. And let me just make a small adjustment here. So what I'm gonna do is I'm gonna explain them, and as I explain them, I'm gonna erase them so that way I have more space. But example number 5, which is on page 202, is actually 5a and 5b. And you have the function g of x equals 3x squared and h of x equals 1/3 x squared. So what does this mean and what am I going to do? Very simple, ladies and gentlemen. First of all, let's review our parent function, and we said that our parent function always passes through the origin. So there you go, this would be your parent function. But if we look at the functions individually, we can determine if they're in fact vertically stretched or vertically compressed. Now, if I look at the first function, it says g of x equals 3 times x squared. So I know that the x squared represents a quadratic function. I know 3 is a constant. Does that mean that 3 is greater than 1? It does. So in reality, what we have here is a vertical stretch by a factor of 3. So we're going to say vertical stretch and I'm just going to say by 3, but you know that means by a factor of 3. So we know that for a fact. So what does that mean? What that would mean is that if I had a table of values, that means that I would multiply every number by 3. But since they're not asking us to make a table of values, you just want us to explain what that is. So basically, it's stretched, so it's a narrow function. So let me write that here real quick. So what that is, just so you guys see, if this is my parent function going through my vertex, a vertical stretch by a factor of 3 is actually a very narrow graph. And what I mean by a very narrow graph is, think of a rubber band. If I'm vertically stretching the graph by a factor of 3, it's kind of like if I was pulling a rubber band upward. So that's why it's kind of like a narrow, especially when you compare it to the parent function. So when you compare it to the parent function, let me erase that real quick. When you compare it to the parent function, and let me distinguish that. When you compare it to the parent function, you see the parent function is here. And let me just identify it so you guys know what I'm talking about. When you compare it to the parent function, it's actually being stretched. So that's why we call it a vertical stretch. So that's about it. Very simple. Again, just to kind of look at it, 3x squared, 3 is in front of the function, it's greater than 1, so it's a vertical stretch by a factor of 3, and what that is just a very narrow graph. We don't need to do anything else because they're not asking us to form a table of values, so what you need to know is very important, is just that it's a vertical stretch by a factor of 3, and more or less just draw a very narrow quadratic function in this case. So that's it for that one. Let's go to the next one. And again, weird noise. There you go, it's live. So the marker just flew off. Alright. So I'm going to leave the description there so you guys understand that this is a vertical stretch by a factor of 3. But if you look at your book, there's another function and it says h of x equals 1/3 x squared. So h of x equals 1/3 x squared. Now this was A, and now we're doing B. H of x equals 1/3 x squared. So we go to our formula, and our formula says, well, first of all, we're going to look at the 1/3 and see if it actually fills out the requirements. So I look at it, it says 1/3. 1/3 is greater than 0, but smaller than 1. So yes, so in reality, what this is a vertical compression by a factor of 1/3. Now, vertical compression, think of the opposite. So stretching, we're pulling it upward. Vertical compression, we're kind of pushing it downward. So let's draw the parent function just so that you guys can compare the parent function. Again, always passing through the origin. And now, a vertical compression by a, so it's right, vertical compression. I'm going to abbreviate that as COMP by 1/3. And what that means is I'm doing this. So I'm actually, the graph is kind of gonna look like this. So this is my parent function. So the graph that this is actually my g of x equals 1/3 x squared. So again, this is my parent function. This is what the compression or the vertical compression of this looks like, which is kind of like, I just kind of pushed it downward, right? So there it is, g of x equals 1/3 x squared, and that's example number 5A and 5B that you can find on page 202. So go ahead, take a look at it real quick. I am going to give you all of 5 seconds before I erase the example. 1, 2, 3, 4, 5, and I'm back. So let's look at the next example. Example number 6. Now in example number 6, we're actually combining stretches and compressions, and we're also combining what we did in our previous video, which was, vertical shift and horizontal shift. Let me fix this real quick. So in example number 6, which I'm going to write here, it says f of x, and example number 6 is on page 203 if I'm not mistaken, or yes, 203. F of x equals 1 minus 2 times x minus 3 squared. Now, there's a lot going in this example because not only do we have a stretching compression, but we also have a shift. We actually have two kinds of shifts, a vertical shift and a horizontal shift. So the first thing that we're going to do is identify our shifts. Now, like I was explaining in the previous video, we're going to look at the parentheses, x minus 3 squared. That x minus 3 actually indicates that we have a graph moving 3 spaces to the right. So the first thing is that I know I'm not going to start at the origin, I'm actually going to start 3 units to the right. We also have in this the 2. And it's not just a 2, it's a minus 2. So what that means is that it's a vertical, or not a vertical, excuse me, it's a reflection across the x-axis. Now I said that if we look at our parent function, our reflection across the x-axis is to take this parent function and then just literally flip it over. So we're going to do that, and let me erase it so that we don't get confused what we're doing. We're going to actually flip over the function, but at 3. Not only that, not only does it have a horizontal shift by a factor of 3, and that's where we're going to draw a little point just to kind of know where we are. We not only have a reflection across the x-axis, which means that the graph is going to be upside down, but we also have a vertical shift. The 1 actually indicates a vertical shift. Now I know it says 1 minus 2, but technically the 1 is a positive number. Since the 1 is a positive number, that means that I'm actually going to move from this 3 1 space up, and it would actually be here. So here is where I would have my graph. Okay, so we have a vertical, and here's my book, and here's my magnifying glass real quick. We have a vertical or shift, or a horizontal shift of 3 units. We have a upward shift of 1 unit, okay? And we also have a vertical stretch by a factor of 2. So we have a reflection because there's a minus sign. We have a vertical stretch by a factor of 2. We have a horizontal shift of 3 units to the right and a vertical shift 1 unit up. So let me recap that before. A lot of you are probably getting confused and not knowing what I just said or did. So we're going to look at this again. We move 3 units to the right. There you go. Because this indicates a horizontal shift of 3 units to the right. There is a 1 outside of it, right? So that 1 actually means that we're actually going to move 3 spaces to the right and 1 space up. There's a reflection because there's a negative sign in front of the 2, which means that the graph is going to be looking upside down. And since the 2, or the absolute value of the 2 is 2, we know that 2 is greater than 1, so that also means a vertical stretch. So when we graph that function, this is more or less what it's going to look like. So once again, let me break it down by parts. I have this function. The first thing I'm gonna look at, just like order of operation, I'm going to work with my parentheses, is x minus 3. That means that there is a horizontal shift of a factor of 3. There's a negative sign here, which indicates a reflection, so that's why the graph is looking upside down. There's actually a vertical shift of 1, because even though there's a minus sign here, technically this number is positive, so that means actually 3 and 1. And then the 2, what we did is, I know that this is a vertical stretch because I took the 2, or the minus 2 if you want, and I got the absolute value of that, which equals 2. And the 2 is greater than 1, so that indicates that there's a vertical stretch. So this is your function of f of x equals 1 minus 2 times x minus 3 squared. So go ahead, take a look at it real quick. I'm going to get your next example before I move on. And I will be back as soon as possible. So that was actually example number 6. Now we're going to do example number 7. And I am going to appear on your screens in the next 3 seconds. So 1, 2, 3, and here I am. So now we're actually going to go to example number 7 on page 204. 4, and that will be your last example for this video. And we're actually going to talk about horizontal stretches or shrinks. Now, example 7a says f of x equals 2x. And 7b, and I'll just write that real quick, is y equals f of 1/2 x equals f of 1/2 x. And let me fix the first one because I think I wrote that one wrong. 7a is y equals f of 2 times x. So y equals, made a mistake real quick. Let me erase that. Y equals f of 2x. And there you go. So let me just double check to make sure I wrote them right. Okay, so horizontal, shrink, or stretch. Now, the formulas are different. As you can notice, in the vertical stretch, it says y equals c times f of x, and in the horizontal stretch or shrink, it says y equals f times c of x. So, we have formulas as well. It says if c is greater than 1, then it's a horizontal shrink by a factor of 1 over c. So, if c is greater than 2, it's actually a horizontal shrink. And a horizontal shrink or compression is like I'm taking the graph and I'm doing this. I'm kind of like folding it or meeting it. So if I look at that one, if I look at it at the first one, all I'm seeing is a horizontal shrink of a factor of 1 over c. So the first one, y equals f of 2x. It's saying that since this is greater than 1, then I actually have a horizontal shrink or compression by 1 over c, and the c is actually the 2, so in reality this is by 1/2. Okay, I just changed the c to 1/2. Now, how does that look graphically? And I'm going to explain that to you real quick. So I'm going to let you take that real quick. So what we have in that case is, now in your books, the function that they use, and you can see this one on page 203, they use this function right here. So when I compress it, this function actually turns into this. Notice how this is the parent function, and you can see this is actually figure 9 of your book. This is actually figure 9. Now when we compress it by a factor of 1/2, we're actually taking the graph and kind of like pushing it towards each other. So this is actually f of 2 times x. So real quick to recap example 7a before I go on to example 7b, is that if I have a graph that looks like this, f of 2 times x, if the 2 or the constant is greater than 1, then would that, first of all, they have to be in a parentheses. Again, just like we were doing the other day. They have to be expressed, not in a parentheses. Let me clarify that. Let me say it differently. They have to be written in this form. If the function is not written in this form, then it's not a vertical, If the function is not written in this form, then it is not a horizontal stretch or shrink, okay? So it has to be written in this format. And if it's written in this format and this number here is greater than 1, then we say that there is a horizontal stretch by a factor of 1 over c, which in this case is by a factor of 1/2. So what you're going to do is you're going to see your parent function and you're going to draw it kind of like coming closer to the y-axis, which is what happened here. So again, if it's written in this form, it's probably some sort of horizontal stretch or compression. If the number 2, or the number inside of the parentheses, or the c, which means constant, is greater than 1, it's a horizontal compression by a factor of 1/2 of 1 over c, which in this case is 1/2. Okay, one last time. f of 2x, it's a horizontal stretch or compression. In this case, it's a stretch because the 2 is actually greater than 1, and that means that it's a horizontal shrink by a factor of 1 over c, which is 1 over 2. Okay, so I'm going to let you look at it real quick and then erase it and then do the last example of the page. Okay, so once again, horizontal shrink in this case because f of 2x actually means that if c is greater than 1, then it's a horizontal shrink by a factor of 1 over c. 1 over c is the same thing as saying 1 over 2, and you draw the graph kind of closing in on each other. All right, so the last one, example 7b, which is also on page 204. 7b on page 204 has the function y equals 1, or f, excuse me, times 1/2 x. So we're going to look at the conditions to see if it satisfies a stretch or a shrink. We know it's horizontal because of the way that it's written, and we can say, it says, if c is greater than 0 but smaller than 1, then we have a horizontal stretch. Obviously, this fills or satisfies those requirements because if you notice, you have c is a fraction. That means that it's greater than 0, but it's actually it's smaller than 1. So that is in this case, horizontal stretch. Okay, it's a horizontal stretch by a factor of 1 over c, and what we say is that it is a horizontal stretch by 2. So the parent function, okay, so again, we say horizontal stretch by a factor of 1 over c, which in this case is 1 over 1/2. And ladies and gentlemen, when you have 1 over 1/2, it's the same thing as saying 2. Because you divide 1 over 1/2, and that turns into 2. So that's why we say horizontal stretch by a factor of 1 over c, or a factor of 2. So if my parent function is like this, which is figure 9 on page 204, that's my parent function. At least that's the parent function that they give you in the book. Now if it's a horizontal stretch, what we're actually going to graph is this. And this is actually y equals f of 1/2 x. So it's a little bit different than what we did previously. Let me recap it real quick. So f of 1/2 x, this is example 7b on page 204. We're going to look at this to see if it satisfies one of the two conditions. It obviously satisfies a horizontal stretch, because the horizontal stretch says that if c is greater than 0 but smaller than 1, then it's a horizontal stretch by a factor of 1 over c, which is what I did here. But the c is actually 1 over 1/2. And when you have 1 over 1/2, it's the same thing as saying 2, because when you divide 1 over 1/2, your answer is 2. So in reality, it's a horizontal stretch by a factor of 2. This is the parent function. And then the stretch would actually kind of look like you're pulling it away. So when you have a vertical stretch, it's like pulling the graph upward. When you have a vertical compression, it's like pushing it downward. When you have a horizontal compression, it's like pushing it downward, pushing it inward like this. And when you have a horizontal stretch, it's like pulling it outward. Okay, so that is it for example 7b. That is it for the examples for this next class. And just like I've said before, you thought you'd get rid of me, but you didn't, because I'm always going to leave work assigned. And the work assigned for this lesson is page 207, problems 41, 43, 47, and then on page 208, problem 71. Guys, when you are done with these exercises, you can email these exercises along with the exercises from the previous class to my emails. You can send them to jmarquez@fbspr.com, and if that one isn't working for whatever reason, you can use the other email account, which is mr.j.marquez which is mr.j.marquez84@gmail.com. You can email me your assignments then, but email them to me once you've done these exercises. So, this is your favorite math teacher signing off. Stay safe, guys. I'm not going to say what you want me to say, but you know it's true. Bye.